Across the vast expanse between Earth and Mars, where sunlight takes minutes to bridge the gap and spacecraft must wait years for the perfect moment to depart, a promise echoes through our collective imagination. It is bold, ambitious, and repeated with such confidence that millions have come to believe it as inevitable. Humans will walk on Mars before this decade ends. Elon Musk has declared it not as a dream, but as a timeline. Starships launching in 2029, boots on Martian soil by 2031, perhaps 2033 at the latest. The vision is intoxicating, a future so close we can almost reach out and touch the red dust ourselves. Yet tonight, as we drift through the physics and engineering that govern interplanetary travel, we must ask a question that demands honesty, not cynicism. Is this timeline a reflection of human determination, or is it constrained by forces far more stubborn than ambition? The promise is everywhere. In interviews, presentations, and social media posts, the narrative unfolds with breathtaking certainty. Giant silver rockets, taller than skyscrapers, will ferry not just astronauts, but entire crews to Mars. They will land, establish bases, and return home, pioneering a new era of multiplanetary civilization. The images are stunning, the rhetoric inspiring, and the confidence unwavering. This is not science fiction, we are told. This is engineering in motion, happening right now, visible in the steel prototypes rising in the Texas desert. Millions believe it. They watch test flights, follow development updates, and plan their lives around the idea that Mars is no longer a distant dream, but an imminent reality. The enthusiasm is genuine, rooted in decades of disappointment with slow-moving space agencies and a hunger for progress that feels tangible, accelerated, and revolutionary. For many, the timeline is not just possible, it is proof that the old limits no longer apply. But beneath the promise lies a labyrinth of physics, engineering constraints, and biological realities that do not bend to optimism. These are not bureaucratic delays or failures of will. They are the immutable laws that govern motion, energy, time, and survival in the void. Tonight, we will journey through these challenges not to diminish the dream, but to understand it more deeply, to see clearly what stands between vision and reality, between announcement and arrival. We will explore the rocket equation, an elegant piece of mathematics that dictates how much fuel is required to escape Earth's gravity and why each additional kilogram of cargo demands exponentially more propellant. We will examine orbital refueling, a concept so complex that no one has yet demonstrated it reliably in space, yet it remains the linchpin of the entire Mars architecture. We will drift through the narrow windows of planetary alignment, understanding why Mars doesn't wait for our schedules, but imposes its own celestial rhythm. And we will confront the invisible threats, radiation, life support, and the psychological toll of months in a confined metal capsule that turn every voyage into a test of human endurance. The question before us is not whether Mars is reachable. It is. The question is whether it is reachable in the time frame being promised, using the systems currently under development, with the realities of physics firmly in place. Is this optimism grounded in engineering progress, or has enthusiasm outpaced what is physically achievable? Is the timeline impossible or merely improbable? Tonight, we will not offer easy answers. Instead, we will walk carefully through each layer of complexity, examining what works, what remains unsolved, and what the evidence suggests about the true pace of progress. The universe does not respond to deadlines. It responds to preparation, precision, and patience. Before we continue deeper into this journey, I'd love to know, Where are you watching from right now? And what time is it where you are? Are you drifting off to sleep under distant stars, or beginning your day with curiosity about the cosmos? Leave a comment below. It's always humbling to know how far our voices travel across this small blue planet we all share. Now, let us begin. The road to Mars is longer than any press conference suggests, and the challenges ahead are as vast as space itself. To understand why Mars remains beyond our immediate reach, we must first look at what exists today, not in renderings or animations, but in metal, fire, and the harsh reality of testing. Starship stands on launch pads in South Texas, a gleaming monument to ambition, towering nearly 400 feet into the sky. It is the largest rocket ever built, designed to be fully reusable, capable of carrying over 100 tons to orbit, and eventually, Elon Musk promises, to Mars. Yet between the towering prototype and a crude mission to another planet lies a chasm so vast that even light seems to hesitate at its edge. As of now, Starship has completed several test flights, each one pushing the boundaries of what this colossal vehicle can achieve. Early attempts ended in spectacular fireballs, explosions captured in slow motion as millions watched. These were not failures in the traditional sense, but data points, lessons written in flame and twisted metal. Later flights achieved more. Starship has reached space, separated its stages, and demonstrated controlled descent. The vehicle has splashed down in the ocean, survived re-entry heat that turns atmosphere into plasma, and landed upright on legs designed to catch it mid-air with mechanical arms nicknamed chopsticks. These are extraordinary achievements, pushing rocket engineering into territories once thought impossible. But reaching space is not the same as reaching Mars, not even close. The gap between what Starship can do today and what it must do to ferry humans across 140 million miles of interplanetary void is measured not in incremental steps, but in exponential leaps of complexity, reliability, and endurance. Every test flight reveals progress, but also exposes the vastness of what remains unsolved. Consider orbital refueling, the cornerstone of any Mars mission using Starship. The vehicle cannot carry enough propellant to reach Mars in a single launch. Physics will not allow it. Instead, the plan requires launching multiple tanker Starships into orbit, each one transferring fuel to a single Mars-bound craft until its tanks are filled. This sounds simple in concept, elegant even, but in practice, it is a ballet of precision that has never been performed. Not once. Not in orbit. Not with cryogenic fuels that boil away in the vacuum of space. Not with vehicles docking autonomously at 17,000 miles per hour. The technology exists in pieces, in simulations, in ground tests. But the complete system, the seamless transfer of hundreds of tons of liquid methane and oxygen between spacecraft, remains untested in the environment where it must work flawlessly. A single failure during refueling could strand astronauts in orbit, or worse, send them spiraling toward Mars without enough fuel to return. Then there is the heat shield, the barrier between survival and incineration. Starship's underside is covered in thousands of ceramic tiles, each one designed to withstand temperatures exceeding 2,500 degrees Fahrenheit during re-entry. Recent flights have shown these tiles can work, at least for Earth re-entry. But Mars re-entry is different. The atmosphere is thinner, the velocities higher, the margins for error vanishingly small. Every tile must remain perfectly bonded to the hull. Every gap must be sealed. A single missing tile on the Space Shuttle Columbia caused catastrophic failure. Starship will have thousands. And unlike the shuttle, which was meticulously inspected before each flight, Starship is intended to fly rapidly, repeatedly, with minimal refurbishment. The heat shield must be not just functional, but resilient beyond anything currently demonstrated. We have seen it survive. We have not yet seen it endure the rigors of interplanetary travel, followed by a Mars landing, followed by a return journey. Landing on Mars presents its own enigma. Starship's landing system has been tested on Earth, where thick atmosphere and familiar gravity allow for controlled descents. Mars offers neither luxury. Its atmosphere is roughly 1% the density of Earth's, providing just enough resistance to create heat, but not enough to slow a massive vehicle effectively. Starship will need to rely almost entirely on its engines, burning through precious fuel while descending through dust and wind toward a surface that may be rocky, uneven, or obscured by storms. No landing system of this scale has ever been tested in Martian conditions. The closest analogy is the Sky Crane that delivered the Curiosity and Perseverance rovers. But those vehicles weighed roughly 1 ton. Starship, fully loaded, will weigh over 100 tons. The engineering challenge is not incremental, it is categorical. Historical comparisons reveal the magnitude of this undertaking. The Apollo program, often cited as humanity's greatest technological achievement, took 8 years from President Kennedy's declaration to Neil Armstrong's first steps on the moon. 8 years of relentless focus, unlimited funding, and the combined efforts of over 400,000 engineers, scientists, and technicians. Yet Apollo was, in many ways, simpler. The moon is 3 days away, not 6 months. There is no atmosphere to navigate, no dust storms to evade, no need for life support systems lasting years. Astronauts could abort and return to Earth within days if something went wrong. Mars offers no such escape. Every component, every system, every backup must function flawlessly for years, in an environment where rescue is impossible. The exponential complexity curve from test flights to crewed missions is steep and unforgiving. Flying an empty Starship to orbit and back is a triumph of engineering. Flying it with propellant transfers, life support, radiation shielding, navigation systems, and human passengers to another planet and back is a triumph of an entirely different order. Each new system introduces failure points. Each failure point must be tested, validated, and certified. And unlike uncrewed missions, where failure is disappointing but acceptable, crewed missions demand near-perfect reliability. NASA's human rating standards require demonstrating success rates approaching 99%. Starship has completed a handful of flights. To achieve human rating, it will need dozens, perhaps hundreds, each one more complex than the last. This is not a critique of ambition. It is a recognition of reality. Starship is remarkable, a vehicle that has already redefined what is possible in rocket engineering. But the distance between remarkable and ready for Mars is measured not in years of development, but in layers of complexity that compound with every new requirement. Each test flight is a step forward, but the horizon keeps receding, revealing new challenges that were invisible from the starting line. As we watch Starship rise from the launch pad, engines roaring, fire and smoke billowing across the Texas coast, we witness not just a rocket, but a promise that one day, perhaps, this machine will carry humans beyond Earth's embrace. But promises, no matter how boldly spoken, must still answer to physics. to engineering, and to the cold, patient arithmetic of space. The current state of Starship is impressive, but Mars remains distant, not just in miles, but in the countless unsolved problems that stretch between here and there. Before we can understand why reaching Mars demands such extraordinary measures, we must first confront a fundamental truth that has governed space travel since the dawn of the rocket age. It is not a truth we can negotiate with, nor one we can bypass through innovation alone. It is mathematics itself, carved into the fabric of how motion works in the universe. This is the rocket equation, and it is both beautifully simple and ruthlessly unforgiving. The equation was formulated by Konstantin Tsiolkovsky in 1897, long before any rocket had touched space. Its elegance lies in its brevity. Delta V, the change in velocity a rocket can achieve, equals the exhaust velocity of its engines multiplied by the natural logarithm of the initial mass divided by the final mass. In simpler terms, how fast you can go depends on how efficiently your rocket burns fuel, and how much of your rocket is fuel versus everything else. This sounds straightforward until you grasp its implications. The equation is exponential. To go twice as fast, you do not need twice as much fuel. You need exponentially more. To go 3 times as fast, the fuel requirements become staggering. And herein lies what aerospace engineers call the tyranny of the rocket equation. Every kilogram of payload demands not just fuel to lift it, but fuel to lift the fuel, and fuel to lift the fuel that lifts the fuel, cascading upward in an unrelenting mathematical spiral. For a journey to Mars, the delta V requirements are immense and uncompromising. Escaping Earth's gravity well and entering a Mars transfer orbit requires approximately 3.8 kilometers per second of delta V from low Earth orbit. Mars orbital insertion demands another 2 kilometers per second. Then, if astronauts wish to return home, they need fuel for Mars departure, approximately 2 kilometers per second, and Earth orbital insertion, another 2.3 kilometers per second. We have not even accounted for trajectory corrections, landing maneuvers, or margin for error. The total delta V budget approaches 12 to 14 kilometers per second, depending on the mission architecture and the specific transfer window chosen. Starship, as currently designed, faces this equation head-on. Its Raptor engines are among the most efficient ever created, burning liquid methane and liquid oxygen with an exhaust velocity that pushes the boundaries of chemical propulsion. Yet even with this efficiency, the mass ratio required for a Mars mission is staggering. A fully fueled Starship weighs approximately 1,200 tons. Of this, roughly 1,200 tons is propellant. The dry mass of the vehicle, the structure, engines, cargo, crew, and life support systems, is about 100 to 120 tons. This presents an immediate problem. A Starship launching from Earth cannot carry enough fuel to reach Mars and return. The rocket equation will not allow it. Even filling Starship's tanks completely provides barely enough delta V to escape Earth's gravity and begin the journey to Mars. To actually complete the mission, the spacecraft must be refueled in orbit, not once, but many times. Current estimates suggest that each crewed Mars mission will require between 8 and 14 orbital refueling launches. Each tanker version of Starship must launch from Earth, rendezvous with a Mars-bound Starship waiting in low Earth orbit, and transfer its propellant load. Only after multiple tankers have made this journey, emptying their fuel into the waiting vessel, Does the Mars Starship have sufficient propellant to depart for the red planet? But the tyranny of the rocket equation does not stop there. Each tanker Starship itself is subject to the same mathematical prison. A tanker launching from Earth with a full load of propellant burns most of that fuel, simply reaching orbit. The fraction remaining for transfer is only a portion of what it carried at launch. Some estimates suggest that each tanker can deliver only 100 to 150 tons of usable propellant to the orbital depot, despite launching with over 1,000 tons of fuel. This creates a compounding problem that many popular discussions overlook. If each tanker delivers only a fraction of its fuel, and the Mars Starship needs over 1,000 tons of propellant in orbit, the number of launches multiplies rapidly. Worse still, some mission architectures require tankers to be refueled by other tankers. A tanker destined to refuel the Mars ship may itself need partial refueling to maximize its delivery capacity. The logistics become a nested sequence of launches, each one critical, each one consuming resources, time, and introducing points of potential failure. Consider the mathematics of just one Mars mission. If the crewed Starship requires 1,200 tons of propellant in orbit, and each tanker delivers 100 tons, 12 launches are needed. 12 flawless launches, 12 flawless rendezvous maneuvers, 12 flawless fuel transfers, all within a narrow window of weeks before the propellant begins to boil off in the vacuum of space. Cryogenic fuels like liquid oxygen and liquid methane do not wait patiently. They evaporate. Active cooling systems can slow this, but they add mass, complexity, and power requirements. The clock is always ticking, and this is for a single mission. Elon Musk has spoken of sending not one, but dozens of starships to Mars in a single transfer window, perhaps even hundreds in future decades. If each ship requires a dozen tanker launches, a fleet of 10 starships would demand 120 launches within a matter of weeks. The scale shifts from ambitious to logistically bewildering. The rocket equation does not care about timelines or aspirations. It does not bend for charisma or capital investment. Every kilogram counts. Every inefficiency is magnified. If the mass of the life support system is underestimated by 10 tons, that is not merely 10 tons of additional fuel needed. It is 10 tons multiplied by the mass ratio, potentially 50 or 100 additional tons of propellant required at launch, which in turn demands another tanker launch, which demands more fuel for that tanker, spiraling outward. Small miscalculations cascade. A slightly less efficient engine burn during one refueling maneuver might leave the Mars Starship with 50 tons less propellant than planned. That shortfall might seem manageable, but in the rocket equation's exponential logic, it could mean the difference between reaching Mars orbit or overshooting into interplanetary space. It could mean the difference between a safe landing and a catastrophic descent. It could mean the crew has enough fuel to return home or must wait years for a rescue mission that may or may not arrive. There is a reason no crewed mission to Mars has ever been attempted. The rocket equation is not a challenge to overcome through willpower. It is a law of physics that defines the boundary between what is possible and what is fantasy. Every space agency that has studied Mars missions has confronted this equation and arrived at similar conclusions. Chemical propulsion alone, even with orbital refueling, pushes the limits of feasibility. Some have proposed alternative propulsion methods: nuclear thermal rockets, ion drives, solar sails. Each offers theoretical advantages, yet each introduces new complexities and remains unproven at the scale required for crewed interplanetary travel. Chemical rockets are well understood, but they are shackled by the rocket equation's exponential hunger for fuel. As we consider the journey to Mars, we must recognize that the tyranny of the rocket equation is not a temporary obstacle. It is the landscape itself. Every mission plan, every spacecraft design, every launch schedule must navigate this terrain. The equation does not negotiate. It does not offer shortcuts. It simply is, silent and absolute, governing the possibilities of spaceflight with the indifference of mathematics. And so, when we hear timelines promising boots on Mars within a handful of years, we must ask, has the rocket equation been satisfied? Have the fuel requirements been met? Have the dozens of tanker launches been accounted for, tested, and proven reliable? Or are we once again encountering the gap between aspiration and the unyielding nature of physics? The rocket equation waits patiently. It has no opinion on deadlines. It merely calculates, and in its calculations, reveals the true cost of reaching another world. In the silence of low Earth orbit, 300 miles above the planet's surface, two spacecraft must meet. Not once, not twice, but perhaps a dozen times or more. Each meeting must be precise, measured in millimeters across distances where a single miscalculation could spell catastrophe. This is not science fiction. This is the requirement for any Mars mission using Starship, and it is a puzzle that has never been solved at this scale. Orbital refueling sounds simple in concept. Launch a Starship filled with fuel. Dock it with another Starship waiting in orbit. Transfer the propellant. Repeat until the Mars-bound ship is fully fueled. Then begin the journey. But between concept and reality lies an abyss filled with challenges so profound that some engineers wonder if we are asking physics for more than it is willing to give. The numbers themselves are daunting. A fully fueled Starship requires somewhere between 8 and 14 separate refueling flights, depending on the final design specifications. Each tanker must launch, reach orbit, rendezvous with the target vehicle, dock with perfect precision, transfer its cryogenic propellant, undock and return. And this entire ballet must occur within a narrow window of time, because the fuel itself is vanishing. Liquid methane and liquid oxygen, the propellants Starship uses, exist in their liquid state only at extraordinarily cold temperatures. Methane must be kept below -161 degrees Celsius. Oxygen, even colder, at -183 degrees Celsius. In the vacuum of space, maintaining these temperatures is a constant battle against thermodynamics. Even with the best insulation humanity can engineer, heat seeps in. From the sun's radiation, from Earth's infrared glow, from the spacecraft's own systems generating warmth, and as heat enters, the fuel boils away. Current estimates suggest that cryogenic propellants in orbital storage lose between 1% and 3% of their mass per day to boil off. This may sound modest, but consider the implications. If the refueling process takes weeks, which it likely will, tens of tons of fuel could simply evaporate into space before the journey even begins. Engineers speak of active cooling systems, of shadow shields that block sunlight, of innovative tank designs that minimize heat transfer. Yet none of these solutions have been tested at the scale required. We are not discussing a small research tank on the International Space Station. We are discussing vessels holding over 1,000 tons of propellant, waiting in orbit while more fuel arrives. The docking itself presents challenges that cascade into complexity. Two massive spacecraft, each weighing hundreds of tons when fueled, must align with extraordinary precision. The docking mechanisms must seal perfectly, creating a connection capable of handling immense pressure as fuel flows between vessels. On Earth, we dock ships in harbors and refuel aircraft on runways, guided by gravity, atmosphere, and the friction that keeps things stable. In orbit, none of these anchors exist. Microgravity transforms fluid dynamics into something alien and unpredictable. Fuel does not simply pour from one tank to another. Without gravity to pull it downward, liquid propellant forms floating spheres, clinging to tank walls through surface tension, behaving more like thick syrup than flowing water. To transfer fuel in orbit, engineers must use pressure differentials, carefully controlled vents, and possibly rotating the spacecraft to create artificial gravity through centrifugal force. But rotating two docked vehicles, each the size of a 15-story building, introduces its own hazards. Structural stress, unpredictable momentum shifts, the risk that something, somewhere, will flex or bend in ways not anticipated. SpaceX has conducted small-scale propellant transfer demonstrations in orbit, moving fuel between internal tanks within a single Starship. These tests are valuable, even essential, but they are to operational refueling what a paper airplane is to a 747. The gap between proof of concept and operational reliability is measured not just in engineering challenges, but in the accumulated wisdom of thousands of successful repetitions. We have docked spacecraft countless times. We have transferred small amounts of propellant experimentally, but we have never combined these tasks at this scale, under these conditions, with this much at stake. Consider the launch cadence required. To assemble a Mars mission, one Starship tanker must launch every few days for months. This is unprecedented. The most ambitious launch schedules in history, during the height of the Space Shuttle program, managed a flight every few weeks at best. Now we are proposing to launch the largest rocket ever built, repeatedly, in rapid succession, each time carrying volatile cryogenic fuel into orbit. Each launch must succeed. Each vehicle must perform flawlessly. A single failure during this refueling campaign could delay the entire mission by years, as the Mars transfer window opens only once every 26 months. The infrastructure required is staggering. Propellant production facilities that can generate thousands of tons of liquid methane and oxygen. Launch pads capable of turning around in days rather than weeks. Ground crews working around the clock. And all of this must function with the reliability of a commercial airline, not the experimental nature of a space program still proving its basic technologies. Then there is the question of what happens when something goes wrong. Not if, but when. All complex systems experience failures. A docking mechanism jams. A fuel line develops a leak. A micrometeorite punctures a tank. In low Earth orbit, with the Mars-bound crew already aboard, waiting for the final refueling operations, what options exist? The crew cannot simply return to Earth if their vehicle is partially fueled with cryogenic propellants, creating pressures and thermal stresses the ship was not designed to manage during re-entry. They cannot wait indefinitely as their life support systems consume resources and the transfer window closes. Some engineers propose contingency plans, backup tankers on standby, automated systems that can complete refueling without human presence aboard the destination vehicle. Launch the crew only after refueling is complete. Each solution introduces new complexities, new costs, new points where reality might diverge from the plan. Perhaps most striking is the gap between current testing and operational readiness. As of now, Starship has demonstrated the ability to reach orbit and return. This is a monumental achievement, one that should not be diminished. But reaching orbit and conducting a sustained orbital refueling campaign are separated by an ocean of engineering maturity. Spacecraft systems must not merely work, they must work reliably, repeatedly, in an environment where there are no second chances. The history of spaceflight teaches us that every major capability requires years, often decades, of incremental testing before it becomes routine. Docking in space took years to perfect. In-orbit assembly of the International Space Station spanned more than a decade, with each module representing lessons learned and systems refined. We are now proposing to compress this learning curve dramatically, to move from experimental demonstrations to operational missions carrying human lives in a time frame that makes some veteran engineers deeply uneasy. Yet it is not impossible. Physics does not forbid orbital refueling. The laws of thermodynamics are strict, but they are not impenetrable walls. With sufficient testing, sufficient resources, sufficient time, these challenges can be overcome. The question is not whether it can be done, but whether it can be done on the timeline proposed, with the reliability required, before we commit human lives to the journey. Orbital refueling remains an unsolved puzzle, not because we lack the vision to imagine it, but because we have not yet done the patient, methodical work required to make it routine. In the grand narrative of Mars exploration, this unglamorous process, spacecraft meeting in the darkness to exchange fuel, may prove to be the most critical chapter. Without it, Starship remains an impressive vehicle capable of reaching orbit. With it, humanity gains the ability to venture beyond Earth's gravitational embrace and sustain expeditions to other worlds. The fuel must flow, the docking must succeed, the timeline must hold. And in the cold mathematics of orbital mechanics, these requirements are not mere goals. They are absolute necessities. The puzzle awaits its solution. The universe does not wait for humanity's ambitions. It moves according to laws older than time itself, indifferent to schedules, timelines, and promises made on social media. When we speak of traveling to Mars, we speak not just of distance, but of cosmic choreography, a celestial dance between two planets that align favorably only once every 26 months. This is the Mars transfer window, and it is not a suggestion. It is a fundamental constraint written into the architecture of the solar system itself. Imagine Mars and Earth as two runners on concentric tracks around the Sun. Earth, closer to the Sun, completes its lap in 365 days. Mars, farther out, takes 687 days. They are constantly moving at different speeds, perpetually changing their positions relative to one another. Most of the time, they are poorly positioned for travel, separated by vast distances that would require impossible amounts of fuel to cross efficiently. But approximately every 26 months, the planets align in such a way that the journey becomes feasible. This alignment is the transfer window, and missing it means waiting another 2 years for the next opportunity. The mathematics behind this window are elegant and unforgiving. They rely on what is called a Hohmann transfer orbit, named after German engineer Walter Hohmann, who calculated these trajectories in 1925. A Hohmann transfer is the most fuel-efficient path between two orbits. The spacecraft fires its engines to escape Earth's orbit, follows an elliptical path that intersects Mars's orbit at precisely the moment Mars arrives at that same point. It is a cosmic rendezvous that must be timed with extraordinary precision. Launch too early or too late, and the planet will not be there when you arrive. The window is not metaphorical. It is a specific period, usually lasting just a few weeks, when the geometry of the solar system permits efficient travel. For Elon Musk's ambitious timelines, the upcoming windows are everything. The 2029 window opens in September of that year. Miss it, and the next opportunity is 2031. Miss that, and it's 2033. Each delay does not merely postpone the mission by months, it postpones it by years. This is the tyranny of orbital mechanics, a schedule dictated not by engineers or billionaires, but by the silent turning of worlds. Consider what a single Mars mission actually entails in terms of time. The journey to Mars, even during an optimal transfer window, takes between 6 and 9 months, depending on the specific trajectory chosen. Once the crew arrives, they cannot simply turn around and come home. They must wait on Mars for the planets to realign, which takes approximately 18 to 20 months. Only then does a return window open. Add another 6 to 9 months for the journey home, and the total mission duration becomes unmistakable: 2.5 to 3 years minimum. This is not a trip. It is an exile, a commitment that removes astronauts from Earth for longer than most military deployments, longer than many prison sentences. Some have proposed faster trajectories to reduce travel time. In theory, spacecraft could reach Mars in as little as 3 or 4 months by burning more fuel and taking a more direct path. But here, physics imposes its exponential price. The fuel required does not increase linearly with speed, it increases exponentially. A trajectory that cuts travel time in half might require 3 or 4 times as much fuel, and that fuel must itself be launched, which requires more fuel, which requires more launches, which multiplies complexity and cost until the mission becomes architecturally unsustainable. The Hohmann transfer is not simply the cheapest option. For missions of this scale, it may be the only realistic option. The transfer window also constrains everything that comes before launch. Testing schedules, refueling demonstrations, crew training, all of it must synchronize with the celestial calendar. If a critical test fails 6 months before a launch window, there is no time to redesign, rebuild, and retest before the window closes. Engineers cannot ask the planets to wait. The window will open and it will close, regardless of whether humanity is ready. This creates a cascading pressure on development timelines. Every delay in one phase of the mission risks missing the entire window, which means waiting another 26 months, which means contracts expire, budgets are re-evaluated, political priorities shift, and momentum is lost. There is also the question of what happens if something goes wrong after launch. Once a spacecraft is en route to Mars during a transfer window, there is no turning back. The trajectory is committed. If a critical system fails 1 month into the journey, the crew cannot simply reverse course and return to Earth. They must continue to Mars, attempt repairs in transit, and hope the systems hold together long enough to reach the surface or survive in orbit until the return window opens. This is not like maritime travel, where a ship can turn around or divert to the nearest port. In space, there are no ports. There is only the trajectory, and the trajectory is absolute. Some mission planners have explored the concept of abort trajectories, paths that would allow a spacecraft to loop around Mars and return to Earth without entering orbit, shortening the total mission time in an emergency. But these trajectories come with their own complications. They require different fuel loads, different launch windows, and they still take many months. In the event of a medical emergency or catastrophic system failure, months may be far too long. Perhaps most profoundly, the transfer window represents a philosophical constraint. It reminds us that space exploration is not simply about building better rockets or securing more funding. It is about humility in the face of cosmic scale. Mars does not care about quarterly earnings reports or public expectations. It orbits the Sun according to laws that have governed the solar system for billions of years, and it will continue to do so long after every rocket we build has turned to dust. The 26-month cycle is a rhythm older than humanity, a cosmic metronome that beats indifferently in the void. To send humans to Mars is to synchronize human ambition with planetary motion, to accept that some deadlines cannot be negotiated, some schedules cannot be accelerated, and some windows, once closed, will not reopen simply because we wish them to, and so we return to the timelines, the projections, the promises of Mars colonies in the 2030s. The transfer windows of 2029, 2031, and 2033 are not distant abstractions. They are fixed points in time, rapidly approaching, each one a binary outcome, launch or wait. There is no middle ground. The cosmos does not compromise. It offers a window, brief and unforgiving, and then it moves on, leaving us to measure our progress, not in months or years, but in the cold arithmetic of planetary alignment. Beyond the engineering of rockets and the mathematics of orbital mechanics lies a challenge that cannot be solved with more fuel or bigger engines. It is the fragility of the human body itself, traveling through an environment that was never meant to sustain life. As Starship ventures toward Mars, carrying its crew across the vast emptiness between worlds, two invisible forces begin their silent assault. Radiation, streaming from the Sun and the depths of space, and the relentless demands of biological survival in a sealed metal container hurtling through the void. These are not problems that announce themselves with alarms or explosions. They accumulate slowly, invisibly, molecule by molecule, day by day, until the damage becomes irreversible. The journey to Mars and back spans anywhere from 2 to 3 years, depending on orbital alignments and transfer windows. During this time, astronauts are exposed to levels of cosmic radiation that dwarf anything experienced on Earth, or even aboard the International Space Station. On Earth, our planet's magnetic field and thick atmosphere shield us from most of this radiation. Aboard the ISS, orbiting within Earth's protective magnetosphere, astronauts receive elevated doses, but still within manageable limits for missions lasting months. Mars-bound travelers have no such protection. They drift through interplanetary space, exposed to galactic cosmic rays, high-energy particles ejected from distant supernovae that stream through the solar system at nearly the speed of light. Current NASA guidelines limit astronaut radiation exposure to levels that increase lifetime cancer risk by no more than 3%. A round-trip Mars mission, by most estimates, would expose crew members to approximately 0.66 sieverts of radiation, dangerously close to or exceeding career limits for many astronauts. This is not a theoretical concern. Cosmic radiation damages DNA directly, increasing the risk not only of cancer, but of cataracts, cardiovascular disease, and potential neurological effects that are only beginning to be understood. Studies on mice exposed to simulated deep space radiation have shown cognitive impairments, disrupted neural pathways, and behavioral changes that suggest the brain itself may be vulnerable in ways we have not yet fully mapped. But cosmic rays are not the only threat. The Sun, our life-giving star, becomes a silent predator beyond Earth's magnetic embrace. Solar particle events, unpredictable eruptions of charged particles from the Sun's surface, can flood the space between planets with radiation levels thousands of times higher than background cosmic rays. These events are sporadic, violent, and currently impossible to predict with more than a few hours' warning. During the 1972 Apollo missions, a massive solar particle event occurred between lunar landings. Had astronauts been on the Moon's surface or in transit at that moment, they would have received potentially lethal doses of radiation. On a Mars mission lasting years, the probability of encountering multiple solar particle events approaches near certainty. Starship's current design includes some shielding, but truly effective protection would require either prohibitively heavy materials or innovative solutions like water-lined walls or electromagnetic deflection systems, none of which have been tested at the necessary scale. The crew would need a dedicated storm shelter, a heavily shielded compartment where they could retreat during solar events, sitting in darkness for days, waiting for the invisible storm to pass. Yet even if radiation could somehow be managed, the challenge of simply keeping humans alive in a sealed spacecraft for years presents obstacles that have never been solved at the required scale. The International Space Station supports crews of 6 or 7, using partially closed-loop life support systems that recycle water and generate oxygen. These systems, refined over decades, still require regular resupply missions from Earth. Water recyclers fail, filters clog, carbon dioxide scrubbers degrade. On the ISS, replacement parts arrive every few months. On a Mars mission, there is no resupply. Every component must function flawlessly, or the crew must repair it with only the spare parts they carried from Earth. Consider water, the most fundamental human need. Current ISS systems recycle approximately 93% of water, recovering it from humidity, urine, and even exhaled breath. That 7% loss must be replenished. On a Mars mission, a crew of 6 would need to achieve near-perfect closure, recycling 98 or 99% of their water for years without failure. A single malfunctioning pump, a contaminated membrane, or a biological fouling event could cascade into catastrophe. The closed-loop systems required for Mars are not incrementally more complex than those on the ISS. They are fundamentally different, operating at efficiency levels that have never been demonstrated in space. Oxygen generation faces similar challenges. The ISS uses electrolysis to split water into hydrogen and oxygen, venting the hydrogen into space. A Mars-bound Starship cannot afford to discard hydrogen. It must capture and recycle every atom, perhaps using Sabatier reactors to combine hydrogen with captured carbon dioxide, creating methane and water in an endless chemical loop. These systems exist in laboratories and on the ISS at small scales, but scaling them to support a crew for years while maintaining perfect reliability is an engineering challenge that remains theoretical. Then there is carbon dioxide, the invisible waste product of every breath. On Earth, we exhale it into an atmosphere vast enough to dilute it into irrelevance. In a sealed spacecraft, CO2 accumulates rapidly, becoming toxic within hours if not removed. The ISS uses chemical scrubbers and mechanical systems to capture carbon dioxide, but even these require consumable materials that must be restocked. Advanced systems can regenerate scrubbing materials, but they consume energy and generate heat, adding to the spacecraft's thermal management burden. Every system supports every other system, and the failure of one can destabilize them all. The psychological dimension of this journey is equally daunting, though harder to quantify. Astronauts aboard the ISS experience isolation, but they orbit a planet they can see from their windows, and they know that in an emergency, they could return to Earth within hours. A Mars crew will watch Earth shrink to a pale blue dot, then vanish into the glare of the sun. For months, they will see nothing but darkness and distant stars. Communication delays will stretch to over 20 minutes each way, making real-time conversation impossible. They will live in a space roughly the size of a small house, with the same 5 or 6 people for years, knowing that any interpersonal conflict cannot be resolved by separation or outside intervention. Research in extreme isolation environments, submarines, Antarctic research stations, suggests that even highly trained individuals experience psychological strain under such conditions. Depression, anxiety, interpersonal conflict, and cognitive decline are not uncommon. On a Mars mission, there is no early return option, no relief crew, no weekend leave. The spacecraft becomes not just a home, but a prison from which there is no escape until the mission concludes. The psychological resilience required is unprecedented in human experience. Medical emergencies present perhaps the starkest illustration of the mission's risks. On Earth, or even aboard the ISS, serious injury or illness can be addressed with evacuation and advanced medical care within hours. A Mars crew member who suffers appendicitis, a dental abscess, a kidney stone, or any of 1,000 other acute medical conditions must be treated by crewmates with limited equipment and training. Telemedicine can provide guidance, but with communication delays, a surgeon on Earth cannot talk a crew member through a procedure in real time. Some conditions that are routine emergencies on Earth, easily treatable with proper facilities, could become death sentences in deep space. The invisible killers are not dramatic. They do not announce themselves with fire or collision. They work slowly, eroding health, straining systems, testing the limits of human endurance. Radiation accumulates in tissues. Life support systems drift toward failure. Psychological stress compounds over months and years. These are challenges that cannot be overcome with better rockets or more ambitious timelines. They require technologies that do not yet exist at the necessary reliability and solutions to problems we are only beginning to understand. In the silent vastness between Earth and Mars, the greatest danger is not the journey's distance, but the fragility of those who attempt to cross it. After months of traversing the void between worlds, after surviving radiation storms and the psychological strain of confinement, the spacecraft approaches Mars. The red planet grows steadily in the viewport, its rusty surface marked with ancient river valleys and towering volcanoes that dwarf anything on Earth. This moment should feel like triumph, like the culmination of human ingenuity and courage. Instead, it marks the beginning of what engineers call 7 minutes of terror. Except, unlike previous Mars landings, what Starship must accomplish may not be terror at all. It may be impossibility dressed in optimism. Mars presents a paradox that has haunted planetary scientists since the first probes attempted landing. Its atmosphere is simultaneously too thick to ignore and too thin to trust. At just 1% the density of Earth's atmosphere, Mars offers enough resistance to generate tremendous heat during entry, enough to incinerate a spacecraft if the angle is even slightly wrong. Yet that same atmosphere is far too tenuous to slow a massive vehicle using parachutes alone. On Earth, parachutes can lower spacecraft gently to the ground. On Mars, they merely reduce catastrophic velocity to merely devastating velocity. Every successful Mars landing to date has been a carefully choreographed dance between heat shields, parachutes, and retro rockets, each system compensating for the limitations of the others. The largest object ever successfully landed on Mars is the Curiosity rover, weighing approximately 1 metric ton. It required a heat shield the size of a small car, the largest supersonic parachute ever constructed, and a complex sky crane system that lowered the rover on cables while rockets hovered above. The entire sequence was executed with millimeter precision, and even then, engineers held their breath until confirmation arrived. Now imagine landing something 100 times heavier. Starship, fully fueled for the return journey, would weigh well over 100 metric tons on Mars. No parachute system could support that mass in Mars's thin atmosphere. No heat shield yet designed has been tested at that scale under Martian conditions. The entire landing must rely on supersonic retropropulsion, firing rocket engines forward while traveling faster than the speed of sound to slow the descent. This technique has never been attempted at such scale on Mars. On Earth, SpaceX has demonstrated supersonic retropropulsion with Falcon 9 boosters, but Earth's atmosphere is 100 times denser, providing different aerodynamic forces, different stability characteristics, different everything. Mars's atmosphere plays tricks on descending spacecraft. The thin air provides little dampening of oscillations. A vehicle that begins to tilt or spin during descent has far less atmospheric resistance to naturally correct its orientation. Computer models can simulate this, but they rely on atmospheric data collected from orbit and from much smaller landers. Scaling those models up to a vehicle the size of a 15-story building introduces uncertainties that compound with every second of descent. And then there are the dust storms. Mars is famous for them. Some are localized, swirling devils that dance across the plains for hours. Others grow to encompass the entire planet, turning day into twilight and obscuring the surface for months. During descent, sensors must identify a safe landing zone in real time, detecting rocks, slopes, and soft soil while traveling at hundreds of meters per second. Dust in the atmosphere scatters laser altimeter beams, confuses optical cameras, and can even affect engine performance if particles are ingested during the final descent burn. Unlike landing on Earth, there is no abort option. On Earth, if something goes catastrophically wrong during a rocket landing, the crew can activate abort systems, deploy parachutes, or in some scenarios, simply crash into the ocean and survive. Mars offers no such mercy. Once committed to entry, the spacecraft must land or be destroyed. There are no nearby landing sites to divert to, no emergency runways, no rescue helicopters waiting below. The landing site chosen months earlier, based on orbital imagery and topographic data, must be reached with precision, regardless of what the crew discovers as they descend. Perhaps most unsettling is the communication delay. Mars is never closer than about 34 million miles from Earth, which means radio signals take at minimum 4 minutes to travel one way. During landing, mission control on Earth can do nothing but watch telemetry from the past. By the time engineers see the spacecraft beginning its descent, it has already landed, crashed, or been incinerated. The crew and the spacecraft's computers must execute the landing autonomously, with no possibility of real-time guidance or troubleshooting from home. This delay transforms every landing into a leap of faith. If an engine fails during descent, the onboard computers must detect the failure, calculate a new trajectory, and compensate using remaining engines, all within seconds. Human pilots aboard cannot rely on instinct alone. They are falling through an alien atmosphere in a vehicle that has never performed this maneuver under these exact conditions, trusting algorithms that have never been tested in this precise scenario. Engine reliability becomes not just important, but existential. Starship uses multiple Raptor engines for landing. The current design philosophy assumes some level of redundancy, that if one engine fails, others can compensate. But at 100 tons, the margin for error shrinks dramatically. Each engine must ignite reliably after months in the radiation-soaked vacuum of space, must throttle precisely in response to computer commands, must continue firing through vibration, heat stress, and the ingestion of Martian dust kicked up by neighboring engines. A single engine failing to reignite or throttling incorrectly for even a few seconds could send the entire spacecraft tumbling. Testing these systems on Earth presents challenges that border on philosophical. We cannot replicate Mars's atmospheric density in Earth's gravity. Wind tunnels can simulate the thin Martian air, but they cannot simulate the gravitational forces of a 100-ton vehicle descending. We can test engines in vacuum chambers and in Earth's atmosphere, but Mars presents a unique combination of low pressure, different gravitational acceleration, and surface conditions that we can approximate but never fully duplicate. Every simulation, every test firing, every scale model contains assumptions that may not hold when the actual landing begins. There is also the terrain itself. Orbital imaging reveals much, but boulders smaller than a meter across, patches of loose soil, subtle slopes that could destabilize a landing, these remain invisible until the final moments of descent. Curiosity used a sky crane precisely because engineers could not guarantee a flat, stable landing zone. Starship must touch down on multiple landing legs, distributing its enormous weight across several points. If one leg settles into soft soil or strikes a hidden rock, the entire vehicle could tip, and with it, any hope of returning home. This is not to say Mars landing is impossible. It is to say that what SpaceX proposes represents a leap in complexity, scale, and risk that dwarfs anything attempted before. The gap between landing Curiosity and landing Starship is not incremental. It is exponential. Where Curiosity's landing was a masterpiece of engineering caution, Starship's landing must be a masterpiece of unprecedented ambition, executed flawlessly with no second chances, on a world that has destroyed more than half of all spacecraft ever sent to its surface. As the spacecraft begins its final descent, the Martian horizon rises to meet it. Dust swirls below. Engines roar in the thin air, their sound strange and muted. In 7 minutes, everything will be decided, not by hope, not by courage, but by physics, precision, and perhaps a measure of fortune that even the best engineers cannot calculate. Long before the first human steps into Martian dust, something else has to land there first. Not a habitat, not a rover, a factory, In situ resource utilization, or ISRU, is the quiet heart of Elon Musk's Mars vision. It is the difference between a heroic round trip and a one-way colonization attempt, between a return ticket and a slow, televised stranding on another world. At its core, ISRU is a simple idea. Instead of hauling all your fuel, air, water, and building materials from Earth, you use what's already there. On Mars, that means turning thin, rusty air and frozen ground into propellant powerful enough to lift a skyscraper-sized rocket off the surface and send it home. If orbital refueling is the technology that gets Starship to Mars, ISRU is the technology that gets it back. Without it, every mission becomes a disposable epic, a fleet of ships that can land but never rise again. To understand why this matters, we need to leave the romance of exploration for a moment and walk into the industrial core of the dream, a chemical reaction humming in the cold Martian night. On Mars, the air is almost entirely carbon dioxide. The ground, especially near the poles and mid-latitudes, hides vast reserves of water ice. In that pairing, engineers see possibility. Because with carbon dioxide and hydrogen from water, you can perform a transformation that has been known on Earth for more than a century. The Sabatier reaction. At first glance, it looks like alchemy written in chemistry's language. CO2 plus 4H2, CH4 plus 2H2O, 1 molecule of carbon dioxide, 4 of hydrogen. Out comes methane and water. For SpaceX, this is not an abstract equation. It is the blueprint for Starship's return fuel. Its Raptor engines drink liquid methane and liquid oxygen. Oxygen is comparatively easy. You can rip it from CO2 using solid oxide electrolysis or from water using electrolysis. Methane is where the Sabatier reaction becomes the star of the show. Imagine a small nuclear plant or a forest of solar arrays powering an automated station. Martian air is sucked in, filtered, compressed. Electrolyzers split water into hydrogen and oxygen. The hydrogen is fed into a Sabatier reactor along with compressed CO2. In its core, over a nickel catalyst at high temperature, bonds rearrange. Methane emerges along with extra water that can be recycled back into the system. The oxygen is separated, chilled, and liquefied. The methane is cooled and liquefied. Eventually, tanks buried in Martian soil begin to fill with the cryogenic liquids that, months or years later, will hurl a fully loaded Starship off the planet. It sounds elegant. It is elegant. But elegance in spaceflight is always paid for with energy. Every part of this process consumes power. Compressing thin Martian air, heating reactors to hundreds of degrees, splitting water, pumping fluids, running cryocoolers for months on end to keep methane and oxygen so cold they behave more like glass than liquid. On Earth, this is an engineering challenge. On Mars, it is an existential one. Where does that energy come from? SpaceX's public materials often show fields of solar panels stretching over the Martian plain. Solar is familiar, scalable, and safe. But Mars is not Arizona. Sunlight there is only about 43% as strong as on Earth. Dust storms can dim the sky for weeks or months. Even on clear days, panels must be cleaned, tilted, maintained. Every watt has to be fought for. Nuclear power offers another path. Compact, reliable, indifferent to dust or night. NASA has worked on small fission reactors like kilopower, designed to produce tens of kilowatts consistently for years. Scale that up, and a nuclear unit could feed an ISRU plant through Martian winters and global dust veils. But reactors bring their own challenges. Development time, regulatory complexity, launch safety, political resistance. As of now, no such reactor has ever been operated in space, let alone on another planet. This is where the dream runs into the clock. Musk's vision depends on something subtle but unforgiving: the timing of fuel production. Starship cannot arrive on Mars, land, and then casually start making propellant for the ride home. The production must already be underway, long before any human climbs aboard. A crewed Starship needs on the order of 1,000 tons of propellant to leave Mars and rendezvous with a transfer orbit back to Earth. To fill those tanks, an ISRU facility has to land in a previous launch window, survive entry and landing, deploy itself, and operate autonomously for months or years. It has to mine or melt water ice. It has to gulp down CO2. It has to quietly fill storage tanks while sending home a simple, crucial message. It's working. The gas is here. You can come. If the numbers are off, if dust cuts solar input more than expected, if a pump fails, if a Sabatier reactor fouls its catalyst, if temperatures swing beyond design limits, propellant production slows or stalls. The next crewed mission window approaches anyway, on a schedule dictated not by human preference, but by celestial mechanics. Mars and Earth align, as they always do, every 26 months. Do you send a crew when your factory is at 40% of its expected output? 60%? Do you gamble that the bugs will be fixed before they need to come home? This is not a cinematic choice made in real time. It's a systems engineering problem with no reruns. Once a Starship is committed to a transfer trajectory, there is no U-turn halfway. The fuel that brings them home must already exist, or be all but guaranteed by proven, resilient machinery. And here is the uncomfortable truth. No ISRU system of this kind has ever been tested on Mars. NASA's Perseverance rover carries a small experiment called MOXIE, a golden box that inhales Martian air and turns CO2 into oxygen. It has proven that we can make grams of oxygen per hour on a planet hundreds of millions of kilometers away. MOXIE is a precious first step, a miniature proof of concept. But Starship does not need grams. It needs hundreds of thousands of kilograms. MOXIE is a toaster oven placed on a bare patch of Martian ground. Starship requires an entire refinery. We have never mined Martian ice at scale. We have never run a megawatt-class power system on Mars, day and night, for years. We have never operated a large-scale Sabatier plant in Martian gravity, temperature, swings, and dust. Every part of the ISRU chain contains unknowns that are currently glossed over by diagrams and concept art. Engineers know this, which is why any serious plan for Mars must wrestle with an unsettling question. What if the ISRU system underperforms? What if it simply fails? Backup plans in spaceflight are rarely glamorous. They're usually overweight, expensive, and absolutely necessary. A cautious architecture might send multiple redundant ISRU units ahead of time, scattered across the same region. It might include extra robotic rovers capable of swapping parts, repairing solar arrays, clearing dust, or even linking separate plants into a shared grid. You can also imagine pre-positioning propellant made on Earth. Uncrewed tanker starships could land with partial fuel loads, serving as an emergency cache. This solves one problem and creates another: mass. Every kilogram of fuel you bring from Earth is a kilogram you cannot devote to other payloads. The dream of self-sufficiency gets delayed, and the number of launches required multiplies. Another contingency is more philosophical: accepting that the earliest human crews may not have a guaranteed return. This is not a technical adjustment. it is a societal one. Historically, explorers have set sail without certainty of coming home. But modern space agencies operate under different assumptions of risk, accountability, and public scrutiny. Saying, "We might not have the fuel to get back," is not a line NASA or any government will endorse easily. The harsh reality is that a single ISRU plant landing before a crew is not enough. The first missions must bootstrap a basic industrial ecosystem on Mars. That means send in not just one reactor, but several. Not just solar panels, but the tools to expand and repair them. Not just pumps and pipes, but spare pumps and spare pipes. In other words, you must ship a small, automated civilization ahead of your astronauts and hope it can stand on its own long enough to welcome them. Each of these elements adds complexity, mass, and time. Development time on Earth to design and test them. Mission time in space to transport them. Operational time on Mars to prove they can work through dust storms, power dips, and mechanical fatigue. None of this makes the dream impossible. It makes it slower. ISRU on Mars is not just a machine humming in isolation. It is the first factory in a frontier economy. If it works, it changes everything. A single successful plant paves the way for more, each expanding the envelope of what can be attempted. More habitats, more vehicles, more science, more risk. If it fails, the consequences ripple outward. Launch windows slip. Crews stay home. Trust in aggressive timelines erodes. Between those outcomes lies a narrow path where boldness and caution have to walk together. Musk's timeline assumes that we can sprint down that path, that we will go from Moxie-sized experiments to city-sized refineries in barely more than a decade. Physics is not offended by this ambition, but it does insist on its own pacing. Complex systems demand iteration. Industrial processes demand redundancy. And Mars, indifferent and silent, will not rush to accommodate a schedule printed on a presentation slide. Somewhere in that thin, cold air, the Sabatier reaction awaits its moment. Somewhere beneath the dust, ice hides in shadowed layers, waiting to be melted, split, rearranged into the breath and fire of a return journey. ISRU is the hinge on which Elon's Mars timeline swings. If it closes smoothly, starships can land, refuel, and rise again, tracing bright arcs back to Earth. If it sticks, even slightly, those gleaming ships become monuments, towering stainless steel obelisks to a civilization that arrived in hope and found itself waiting on chemistry and power that never quite caught up. The closer we bring Mars from fantasy into engineering, the more a new kind of gravity begins to pull on the mission. Not the gravity of planets or stars, but the gravity of rules, institutions, and human limits. It does not bend space, but it bends plans. It stretches timelines, redirects trajectories, and sometimes, quietly, it stops rockets on the launch pad before they ever see the sky. Up to now, our journey has followed equations, trajectories, and tonnage. But there is another map that must be navigated, drawn not in kilometers and delta V, but in laws, risk thresholds, political realities, and human psychology. It is invisible from orbit, but every real mission must pass through it. If physics is unforgiving, bureaucracy is unignorable. On paper, the path to Mars seems simple. Build Starship, refuel in orbit, launch when the transfer window opens, land, refuel again, repeat. In reality, each of those arrows on the diagram crosses through committees, regulations, signatures, and debates that have nothing to do with rocket engines, and everything to do with what we, as a species, are willing to risk. We begin with an unlikely gatekeeper, NASA. For decades, NASA has refined its safety standards the way a spacecraft refines its trajectory, with every disaster leaving a tiny, permanent correction. Apollo 1, Challenger, Columbia. Each loss of crew etched more caution into the culture. Today, when NASA plans a crewed mission, it does not just ask, can the rocket reach the destination? It asks, what is the probability this crew is alive at the end of the mission? And it answers that with numbers. For the Artemis program, NASA's current roadmap back to the moon, formal requirements like loss of crew probability are tracked, simulated, reviewed. Design choices are evaluated against strict thresholds. Redundancy is not an optional upgrade. It is a baseline expectation. Every new system must be analyzed, tested, and independently verified before a human is allowed to ride it. SpaceX, on the other hand, operates with a different philosophy: fly fast, break things, learn quickly. With uncrewed Starship tests, this works powerfully well. A vehicle explodes, data is gathered, software is updated, hardware is improved, and the next prototype rolls to the pad. In the world of satellites and steel tanks, this is agile innovation. In the world of human lives, it becomes something else. To launch people to Mars on Starship, one of two things must happen. Either NASA moves its risk tolerance dramatically towards SpaceX's approach, or SpaceX moves its entire philosophy closer to NASA's. Neither shift is quick. Both are political. There is also the question nobody can sidestep forever. How many human lives are we actually willing to lose? Early concept talks about Mars often carry the tone of frontier myth. People will die, Elon Musk has said, framing it as a reality of exploration, much like sailing across unknown oceans centuries ago. But it is one thing to say this in the abstract, another to recruit a real crew, sign real documents, look real families in the eye, and send a ship knowing that likely loss of crew is not a rounding error, it is the central estimate. NASA's astronauts operate under risk, but it is risk surrounded by layers of mitigation and oversight. They are not volunteering for a one-way suicide mission. They are participating in a tightly controlled, internationally watched program built to bend odds in their favor. When NASA flies, the world expects astronaut dies to be a tragedy, not an assumption. A Mars Starship, on the timeline often described publicly in the first few windows, might instead be closer to an experimental aircraft in the 1940s. High risk, high uncertainty, and only partially tamed by test data. Where do you find people willing to accept that? They must be highly trained, physically capable, psychologically stable, able to operate complex systems under pressure, yet also willing to sign up for odds that might look, on paper, worse than a combat deployment. The Venn diagram of qualified astronaut candidates and comfortable with a meaningful chance of never coming back is not empty, but it is not large either. And it does not end with the volunteers. Legislators, oversight committees, and international partners all have a say in whether such a mission is politically survivable. One fatal Mars mission could reshape space policy for decades, the way Challenger reshaped the shuttle program. The first crew to Mars will not just be human beings, they will be symbols. When they live, when they struggle, when they die, all of it will be replayed before billions of eyes. Behind all of this sits a quieter, older framework: international space law. We often imagine Mars as a blank slate, a place where one visionary company or one determined billionaire can simply plant a flag and begin. But Mars already exists inside a legal constellation built in the aftermath of the Cold War. The 1967 Outer Space Treaty, ratified by almost every spacefaring nation, states clearly that no country can claim sovereignty over celestial bodies. Space is not a new set of national territories. It is, in theory, a global commons. SpaceX is not a country, but it is a company licensed by a country. Any human mission launched from US soil on a US rocket falls under US jurisdiction and international obligations. That includes not just property rights, but something more subtle: planetary protection. For decades, planetary protection protocols have guided how we send robots to other worlds. Sterilization requirements, contamination controls, landing site restrictions, all designed to minimize the risk of carrying Earth microbes to potentially habitable environments, or bringing unknown biology back home. The idea is simple. Don't ruin the science before we even understand what's there. Don't accidentally seed another planet with Earth life, and then later claim to have found alien microbes. Mars is a prime target for these rules. It may once have hosted oceans. It still might have subsurface pockets of water, brines, or ice with interesting chemistry. Current protocols, managed through bodies like COSPAR and implemented by agencies like NASA and ESA, place strict conditions on where and how we land. Now imagine that, instead of a carefully sterilized rover, we decide to send 100 unsterilized humans, each carrying trillions of microorganisms, along with soil, food, waste systems, leaks, accidents, and all the mess of life. From a planetary protection perspective, this is equivalent to opening every window and door on a gleaming clean room and inviting in a rainforest. To make Musk's Mars colony vision legal under current norms, one of two things must occur. The world must agree to dramatically loosen planetary protection on Mars, accepting that we may forever blur the line between native Martian life and imported Earth biology. Or SpaceX must operate under a stricter regime than any current concept art suggests, with carefully chosen landing regions and strict contamination barriers between human habitats and scientifically sensitive zones. Neither path is trivial. Both involve lengthy international negotiation. Suddenly, the schedule is not just build faster, it is convince more than 100 nations to rewrite or reinterpret the rules. Back on Earth, long before Starship has to satisfy space law, it must satisfy something more mundane: environmental law. Each Mars mission, under current concepts, may require dozens to over 100 Starship launches for crew, cargo, and orbital refueling. Each launch means noise, emissions, risk to local ecosystems, and impacts to communities near the launch site. In the United States, projects of this scale run through environmental impact assessments, public comment periods, lawsuits, negotiations with local and federal agencies. We have already seen this with early Starship tests in Texas, where debris fields, brush fires, and wildlife concerns brought legal challenges and reviews. Now scale that to Mars campaign level. Frequent heavy lift launches year after year. Every launch window becomes not just an engineering sprint, but a regulatory one. How much carbon and soot are injected into the upper atmosphere? What is the acoustic footprint on surrounding towns? How do exploding test vehicles affect protected habitats? These are not abstract questions. They become grounds for injunctions, delays, and operational constraints. The physics of refueling Starship in orbit may be solved in a decade. The environmental approval for turning a coastal region into an interplanetary freeway could easily stretch longer. Then, there is the world of insurance and liability, an invisible layer that sits between ambitious PowerPoints and actual operations. Whenever a rocket launches today, there is a complex web of financial instruments behind it. Insurance for the payload. Insurance for third-party damage on the ground. Liability caps aligned with national regulations. For routine satellite missions, these frameworks are well established, and the risks, while significant, are bounded by history. A crewed Mars mission changes that calculus. Not just because human lives are involved, but because the mission is not a quick orbital ride with immediate rescue options. It is a multi-year commitment with no practical abort mode. If a catastrophic failure strands a crew in Mars orbit with no fuel to land, or in low Earth orbit with a leaking life support system and no backup vehicle, who is liable? The company, the government that licensed the launch, the international partners who contributed hardware. If a Starship failure on ascent spreads debris over neighboring communities, or a booster failure damages critical infrastructure, what level of liability does SpaceX or its investors accept? At some point, the potential cost of a worst-case scenario stops being a line item and starts to look like an existential threat to the company itself. Historically, this is where governments often step in, assuming part of the risk through indemnification or caps. But there is a political price for that. Once taxpayers are on the hook for whatever happens, they tend to demand more say in what is allowed to happen. Overlaying all of this is a question of geopolitics. The image of one privately led Mars settlement operating under a single billionaire's vision seems clean in concept art. In international affairs, it is anything but. If SpaceX establishes the first permanent human presence on Mars, even as a nominally private venture, it will be perceived as an extension of US influence. Other nations may see this as a de facto claim, even if the Outer Space Treaty says otherwise. They may react with rival projects, new alliances, or attempts to slow the mission through regulatory pressure at the United Nations. There are also more subtle implications. Who sets the rules for behavior on Mars? For resource extraction? For conflict resolution between different habitats, should they arise? For the treatment of scientific sites and potential native ecosystems? A privately drafted Mars Constitution might sound visionary, but on Earth, such a document would be read as a political statement, not just a philosophical one. And then there is Elon Musk himself, a polarizing figure involved in social media, AI, automotive, national security contracts, and more. Any crisis on Mars, a failed mission, a habitat accident, an ecological mishap, will not be judged solely as an engineering failure. It will also be interpreted through lenses of global power, corporate influence, and public trust. All of these forces, regulations, safety cultures, environmental reviews, planetary protection, insurance, geopolitics, form a landscape just as real as the craters and dunes of the Martian surface. They do not obey Newton's laws, but they follow their own inertia. Institutions change slowly. Treaties update in years, not launch cycles. Public opinion can swing in a day, but it takes decades to build the resilience to weather those swings. This is not to say that Mars is unreachable because of paperwork. It is to recognize that timeline is not only a question of engines and fuel, it is also a question of consensus. When we imagine a Starship streaking outward during a perfect transfer window, we are picturing the endpoint of thousands of quiet approvals, risk calculations, legal arguments, environmental studies, diplomatic compromises, and human decisions about what level of danger is acceptable in the name of exploration. Only when those invisible orbits align with the celestial ones does a mission truly become possible. So if Elon Musk's vision of Mars feels squeezed by the constraints of physics, it is also compressed by something less visible but equally powerful: the limits of what our current civilization, with its values and institutions, is willing to attempt. To see what a more realistic future might look like, we have to merge both maps, the one drawn by rockets and the one drawn by humans, and ask not just, can we get there, but how and when will we really choose to go? Time in space exploration is a strange thing. On slides and live streams, years are shuffled like cards. 2026 becomes 2028, then before the end of the decade. But rockets do not listen to press conferences. They listen to physics, to metallurgy, to the stubborn reality of complex systems that fail in ways we never anticipated. To understand what is actually possible, we have to leave the world of headlines and enter the slower, quieter clock that all space programs eventually obey. Elon Musk has spoken of 1 million people on Mars before the end of this century, of cargo flights in the mid-2020s, of the first crew perhaps not far behind. These predictions are not made in bad faith. They are made from a place of intense urgency, a belief that humanity must become multiplanetary as quickly as possible. But if we look not at intentions, and instead at track records, a different pattern appears. SpaceX has always been aggressive with its timelines. The Falcon Heavy was announced in 2011, with a first flight expected as early as 2013. It actually flew in 2018. Crew Dragon was discussed in the early 2010s. Its first crewed mission to the International Space Station took place in 2020. Starship itself was, at one point, imagined taking cargo to Mars in the mid-2020s. We are still in the era of iterative test flights and incremental progress to orbit. The pattern is clear. SpaceX tends to be directionally right and temporally optimistic. What they promise often happens, but later, after the hardware has failed, been rebuilt and learned from. This is not a criticism. It is how frontier engineering works. The problem only appears when we mistake the first optimistic slide for a schedule the universe is obligated to respect. So what does the universe actually allow? To glimpse that, let's walk forward through time, not with marketing, but with milestones. By 2030, Starship will almost certainly not be just a sketch on a whiteboard. If the current pace of testing continues, even with setbacks, it is reasonable to expect a fully orbital Starship system, capable of reaching space, returning, and flying again. Not flawlessly, not with airline-like reliability, but with the rough, scarred competence of a workhorse still learning its trade. In this time frame, the most physically plausible achievements look like this: uncrewed Starship flights reaching orbit routinely, testing re-entry profiles, and gradually expanding the envelope of what is safe to attempt. Experimental orbital refueling demonstrations in Earth orbit, perhaps starting with small propellant transfers between tankers, building toward the dream of fully refueling a Mars-capable Starship. Cargo-only missions to the Moon and cislunar space, likely in partnership with NASA's Artemis program, where Starship serves as a lunar lander or heavy cargo hauler. These are not footnotes on the way to Mars. They are prerequisites. Before we can trust a ship to cross tens of millions of miles of empty space we must first prove it can perform the delicate dance of fuel transfer in orbit, survive multiple re-entries, and operate in the harsher radiation and thermal environment near the Moon. NASA's own timelines echo this more patient pace. Artemis aims to return humans to the lunar surface in the mid to late 2020s, then build a more permanent presence into the 2030s, a small station in lunar orbit, repeated sorties to the surface, experiments in long-duration habitation and resource use. China, too, is methodically stepping outward, with a modular space station in low Earth orbit already operational. Their plans include crewed moon missions in the 2030s and eventual robotic and possibly human missions to Mars as their capabilities grow. By 2030, the solar system will likely feel more crowded than ever before, but still, perhaps, entirely without human footprints on Martian soil. This is not a failure. It is the scaffolding. Stretch the timeline a little further to 2035, and something begins to shift. The incremental steps that seemed mundane at first, lunar sorties, orbital depots, robotic missions, start to knit together into an architecture. By the mid-2030s, if things go well, we could see long-duration crewed missions in CS lunar space where astronauts live for months at a time in conditions partially analogous to a Mars transfer. Their bodies and minds become experiments in adaptation. Lunar bases, small modular habitats, testing closed-loop life support systems, partial in-situ resource utilization, and surface operations. Everything from dust mitigation to psychological support is rehearsed on a world only 3 days away, not 6 months. Automated Starship-class landers touching down on Mars with increasing reliability. At first, they bring scientific payloads and rovers. Later, they bring infrastructure, power systems, communications relays, experimental ISRU plants to wring oxygen, water, or fuel from the Martian environment. These robotic landings on Mars are not just science missions. They are rehearsals for survival. Every touchdown tests guidance algorithms, landing engines, and the interaction between Mars' thin atmosphere and a massive heavy lander. Each successful descent carves a path in the invisible mathematics that future crewed vehicles will follow. By this stage, SpaceX might, in an optimistic but not impossible scenario, have demonstrated Starship refueling in orbit at operationally meaningful scales. Multiple uncrewed Mars cargo deliveries, perhaps clustered around favorable launch windows. Extended Starship flights in Earth orbit or to lunar vicinity. Staying in space for months to simulate the conditions of an interplanetary journey. The date on the calendar may still say 2035. But in terms of capability, humanity will have stepped into a new era. Not yet Martian, but rehearsing, over and over, for a crossing we only want to make once with fragile human lives. Beyond 2035, the curve steepens. By 2040, the phrase physically plausible begins to encompass something we can name without flinching. The first crewed Mars mission. Not a city. Not 1 million people, not a self-sustaining civilization. A single expedition, perhaps a handful of astronauts, launched in one or several starships or in a hybrid architecture that blends NASA heritage hardware, international contributions, and private vehicles. What could be in place by then under a realistic but ambitious scenario? A mature Starship system with hundreds of flights behind it, including numerous partial failures that taught engineers what not to do. Operational orbital fuel depots, potentially serving not just SpaceX, but other vehicles, platforms where propellant is stored, transferred, and managed like a new kind of celestial logistics hub. A network of robotic assets on Mars, pre-landed habitats, power grids using solar or small nuclear reactors, communication networks, and early ISRU plants already caching water, oxygen, and maybe methane fuel. Lunar infrastructure serving as a training ground and partial proving site, with crews rotating on and off long-duration missions in a lower gravity, high-risk environment that still allows rescue or return. By 2040, the physics of such a mission are not speculative. They are well understood today. The barriers are engineering maturity, industrial capacity, funding, and global willingness to accept substantial risk. Which leads us to the uncomfortable but necessary question: why do so many experts quietly place the first realistic crewed Mars mission not in the 2020s or even 2030s, but in the 2040s or 2050s? It is not because of a lack of creativity. It is because when you add up the unsolved puzzles, orbital refueling, long-duration life support, radiation shielding, entry and landing of extremely heavy vehicles in a thin atmosphere, robust ISRU, you discover that each of these is not a minor hurdle. Each is a multi-year, sometimes multi-decade effort. None of them exists in isolation. They interlock. You cannot fully design your life support system until you know how often you can resupply and with what mass margins. You cannot finalize your entry profile until you know the exact shape and mass distribution of your landed hardware. You cannot know what ISRU system to scale until you have ground truth data from the exact landing sites you intend to use. Physics allows Mars missions in the 2040s or 2050s because that is the timescale on which complex, safety-critical technologies have historically matured, from early jet engines to nuclear power plants to crewed spaceflight itself. From the first tentative orbits of Vostok and Mercury to the International Space Station took roughly half a century. From Apollo's brief visits to the Moon to the current plans for sustained lunar presence is another half-century. These timescales are not arbitrary. They reflect how long it takes for an entire civilization to solve problems in layers: materials science, software reliability, launch cadence, economic models, international treaties, and human psychology. Mars will likely demand nothing less. Yet, there is another truth we must hold alongside this slower, more sober timeline. Ambitious dates, even unrealistic ones, serve a purpose. When Elon Musk says he wants 1 million people on Mars, he is not providing a precise forecast. He is aiming a spotlight into a distant decade and daring others to walk in that direction faster than they otherwise would. Historically, bold, almost reckless proclamations have often preceded genuine progress. John F. Kennedy's promise to reach the moon before this decade is out was, on paper, an audacious bet against a mountain of unknowns. The timetable was barely met, not because the date was realistic in 1961, but because declaring it forced an immense mobilization of talent, money, and political will. Ambitious timelines compress attention. They put pressure on complacency. They inspire young engineers and scientists who might otherwise choose safer, more predictable fields. The danger only comes when we confuse inspiration with obligation, when we treat a slide with 2029 written on it as a contract with nature, rather than as a directional arrow. While SpaceX pushes outward with this adrenaline-charged approach, other players are moving under different clocks. NASA's Artemis program is deliberately incremental. Each mission builds on the last, with international partners, Europe, Japan, Canada, and others, contributing critical pieces. China's space program is more opaque to the public, but no less serious, systematically ticking off milestones: space station, lunar sample return, heavy lift rockets, robotic Mars missions, and eventually human explorers. It is possible, perhaps even likely, that the first humans to Mars will fly under a patchwork of flags and logos. A NASA-certified life support system in a SpaceX-launched transport with European or Japanese components, Chinese experience informing surface operations, and private companies building habitats, rovers, and power systems. Frontiers have a way of forcing cooperation, even when politics on Earth resist it. The International Space Station, born out of former Cold War rivals, stands as a quiet monument to that. In such a future, the question of whether Elon Musk was right or wrong about the exact year of the first Mars landing begins to lose its power. Timelines, after all, will blur. Delays will accumulate. Surprises, some good, some tragic, will reshape plans again and again. When humans finally step onto Martian soil, the world will not pause to litigate old tweets. It will be too busy watching the red dust billow under human boots for the first time. What will matter then is not who guessed the date correctly, but who helped bend the arc of possibility in that direction. The regulators who quietly modernized rules to allow rapid launch operations without compromising safety. The scientists who refined radiation models. The engineers who made engines that could reignite reliably after thousands of cycles. The people who argued persuasively that space is not a luxury project, but a long-term investment in resilience, knowledge, and perspective. In that light, the journey to Mars is already underway, even if no one has left Earth orbit yet. Every test flight that ends in a fireball is not just a failure. It is a data point on a path that no one has ever walked. Every slipped schedule forces deeper thinking about assumptions. Every mission to the moon or to an asteroid teaches us how human bodies and minds respond to distance, isolation, and alien worlds. Mars will not be won by a single company, a single country, or a single decade. It will be the sum of thousands of decisions, some visionary, some mundane. It will be built out of launch manifests and line items in budgets, out of late-night simulations and quiet debates in rooms most of us will never see. The stars do not rush. They wheel overhead at their own pace, as they did for the first humans who looked up and wondered. Our challenge is not to force Mars to fit inside one person's calendar. It is to align our ambitions with the slow, exacting discipline that physics demands, and to keep walking forward anyway, knowing that even if the dates slip, the direction is sound. In the end, the real story is not whether Elon Musk's Mars timeline is off by 5 years, or 10, or 20. The real story is that for the first time in history, we are close enough that such timelines can be argued about at all. That is the clock that truly matters. Not a launch date on a slide, but the epoch we have entered as a species, the one in which, when we reach Mars, has replaced if as the question. And in that sense, every realistic delay and every impossible promise are part of the same unfolding narrative, a long, patient conversation between our dreams and the unbending laws of the universe, carried out across decades, in the thin air where rockets rise. We have travelled a long way in this episode, though we never left Earth. Instead, we orbited around a different kind of planet, a promise that humans will walk on Mars in just a few years. that a fleet of silver ships will rise from the Texas coast and redraw the map of human history on a red world. Along the way, we passed through the gravitational fields of equations and engineering, of biology and bureaucracy. Each one bent the trajectory of that promise, just as surely as Jupiter bends the path of a passing spacecraft. When we look back across the journey, certain landmarks stand out. We saw that Starship, as it exists today, is not a Mars vehicle. It is a test article, a prototype. Its heat shield tiles crack. Its engines fail. Its launch infrastructure is still being invented as it is used. None of this is a criticism. It is simply the phase of the story we are in. You cannot skip from first draft to masterpiece without writing the middle chapters. We encountered the rocket equation, that quiet tyrant of space travel. It does not argue, it does not negotiate. It simply states that to go faster, to carry more, to land and then leave Mars again, you must pay an exponential price in propellant. The grand images of hundreds of people on Mars compress, under the weight of that equation, into something more modest. A few tons of payload, a handful of crew, if everything goes right. We examined orbital refueling, the beating heart of the Mars architecture. Dozens of tanker flights, cryogenic fluids that must be transferred in weightlessness without boiling away. A ballet of docking maneuvers that has never been performed, at a tempo humanity has never attempted. Without this, the Mars mission is not just delayed, it does not exist. We watch the Mars transfer window flicker on like a cosmic traffic light. Opportunities opening only once every 26 months. Immovable on any schedule slide deck. Even if hardware were ready, even if regulators stamped every page with instant approval, the planets would still insist on their own timing. We floated through invisible hazards, cosmic rays, solar storms, the slow erosion of minds and bones trapped in a pressurized can for months. Life support systems that must run for years without a catastrophic pause. Radiation shielding that is not a graphic in a presentation, but mass on a launch manifest. We drop through the thin Martian atmosphere, where 7 minutes of terror becomes something harsher. 7 minutes for which we do not yet have a proven method at Starship scale. Supersonic entry, hypersonic heating, supersonic retropropulsion, landing legs in dust and rock. Each step is a research program masquerading as a checklist item. We stood on the red ground and realized that making fuel there, ISRU, is not a switch we flip, but an industrial ecosystem we have never built off-world. Chemical plants that must start cold, alone, with no supply chain and no rescue ship waiting just over the horizon. And surrounding all of it, like the faint glow of distant rings, the softer but equally real forces. Regulations, safety certifications, workforce training, psychological readiness, political will. The human systems that must accelerate at the same pace as the rockets, but rarely do. Put together, these are not reasons Mars will never happen. They are reasons Mars will not happen on the advertised timeline. Yet there is something important here. The fact that the timeline is physically impossible does not mean the dream is meaningless. Bold visions act on society the way Jupiter acts on passing spacecraft. They bend trajectories. They accelerate quiet, practical work that would otherwise take decades longer. Without Musk's aggressive Mars rhetoric, would we have reusable boosters landing on ships at sea, private capsules flying crew, an entire new generation of engineers obsessing over cryogenic tanks and heat shields? Perhaps, but likely not this fast. Inspiration is not the enemy of realism. The danger only appears when we confuse the poster for the blueprint, when estimated dates are treated as destiny instead of provocation. Understanding the constraints is not an act of cynicism. It is how dreams survive contact with reality. When we account honestly for propulsion, for refueling, for biology and bureaucracy, the picture that emerges is slower, smaller and far more fragile than the marketing promises, but it is also more durable because it is anchored in what physics will allow. So the real question is not, will Musk put a city on Mars by 2030? It is, what can humanity actually achieve if we respect the laws of nature as partners instead of obstacles? How much safer, more sustainable, and more inclusive could our push outward be if we plan for the universe we live in, not the one we wish we lived in? Maybe the first crewed Mars mission is not 100 people, but 4. Maybe it does not leave in the next window, or the one after that, but later in this century. Maybe the first flights are not triumphant colonizations, but careful, reversible experiments like Apollo, but with more humility and more attention to the long game. From a certain angle, that is not a downgrade. It is a path that gives us time to solve radiation, psychology, governance, and ethics before we scatter fragile human lives across 2 planets. It is a way of saying, we intend to be a multi-planet species, and we intend to still be one in 1,000 years. As you drift out of this video and back into your own orbit, your room, your commute, the glow of your screen, I'd like to invite you to add your own trajectory to this conversation. If you found this exploration thought-provoking, please take a moment to like the video. It genuinely helps push it out to more curious minds who might be asking the same questions. Let me know in the comments where you're listening from. What city, what country, maybe even what time of night. And tell me, in your view, what is a realistic year for the first human footprints on Mars, and what must we solve before we go? If you'd like to go a step further in supporting these deep dive, sleep-friendly science journeys, there is an optional YouTube membership available. It's completely voluntary, but it helps keep the channel independent and allows me to spend more time on research, writing, and production. You can click Join below the video to see the details. Again, entirely optional, and just watching, liking, and commenting already means a lot. The future of Mars is not written yet. It will not be decided by one person, one company, or one deadline. It will be shaped by a civilization learning, slowly and imperfectly, to work with the universe instead of against it. Dreams give us the direction. Physics sets the route. What we do next, how carefully, how honestly, how bravely we walk that path, will determine whether Mars becomes a brief stunt or a lasting chapter in the long unfolding story of life in the cosmos. For now, close your eyes if you like, and imagine that distant red world not as a promise broken by a rushed timeline, but as a destination patiently waiting for when we are truly ready to arrive.